Good morning. See this problem. It is continuation for yesterday class. Again, we can start from starting. A random noise x of t having a power spectral density sxx of omega is equal to 3 divided by 49 plus omega square is applied to a network which is h of t is equal to u of t into t square e power minus 7t. The network response is denoted by y of t. So here the system is a network. The input is x of t, a noise signal, random noise signal, and it has a power spectral density of d divided by 49 plus omega square. If you apply this x of t for a network, getting the response or output is y of t. So the y of t, for an LTI system, whenever it is subjected to random process, y of t is equal to convolution of x of t with h of, there is a h of t into convolution with h of minus t. So there is a convolution operation, two convolution operations in time domain. So it will get in frequency domain is syy of omega is equal to magnitude of h of omega whole square into sxx of omega. It is already, we know this formula. Now here, first he has asked that what is the average power in x of t? What is the average power in x of t? So average power means we are going to be obtained from, it is from frequency domain. He has given this power spectral density also. So if we calculate Rxx of tau, and if we substitute tau is equal to 0, it is nothing but average power of x of t. So you know Rxx of tau is nothing but inverse Fourier transform of sxx of omega. So inverse Fourier transform of sxx of omega is equal to, you write this formula. What is the inverse Fourier transform of sxx of omega? 1 divided by 2 pi integral minus infinity to infinity sxx of omega into e power j omega tau into d omega. It is our inverse Fourier transform of sxx of omega. It is nothing but Rxx of tau. Now, for getting this calculation of power, we are going to substitute tau is equal to 0. So, whenever tau is equal to 0, the e power j term is 1. So, you will get this one. Already we discussed in the previous class also. Integral minus infinity to infinity 3 divided by omega square plus 7 square. 49 we are representing like 7 square into d omega. Nothing but 1 by a. It is like a formula 1 divided by a square plus omega square. It is formula is 1 by a tan inverse of omega by j. Now you substitute, there is a limits are minus infinity and plus infinity. So if you substitute plus infinity, you will get pi by 2. If you substitute minus infinity, you will get minus pi by 2. Pi by 2 of minus pi by 2, it is the pi. So it is the average power. Now coming for this one, it is important here. The output response in frequency domain is syy of omega is equal to magnitude of h of omega whole square into sxx of omega. So this magnitude of h of omega whole square, if you know h of omega, that is nothing but transfer function of the system. Nothing but transfer function of the system. You will get the magnitude of h of omega whole square. So what is the transfer function of the system? It is nothing but h of omega. It is nothing but Fourier transform of given impulse response. So impulse response already he has given for the given network. It is the impulse response. If you apply Fourier transform for this impulse response, you will get the h of omega. Now, what is the Fourier transform of this one? Usually, by using this general formula, it is somewhat complicated because it is a t square. That's why my suggestion is go for Laplace transform. Go for Laplace transform. You know the Laplace transform standard formulas. Whenever there is a t power n u of t, whenever there is a t power n u of t. The Laplace transform is n factorial by s power n plus 1. So for addition for this, whenever there is an exponential term, suppose there is e power minus at, the s is going to be replaced with s plus a according to shifting in s domain property. And suppose this e power at is there, that is s is going to be replaced with s minus a. So based on that formula, we are going to be write this n factorial by s plus a whole power n plus 1. Now, what is the relation between Laplace transform and Fourier transform? S is equal to, if we substitute S is equal to j omega. My sincere suggestion is, before applying Fourier transform, you better apply Laplace transform for this. After obtaining the Laplace transform, whenever there is a S, we are going to be replace S with j omega. That is my suggestion. So then only we are going to get, it is very easy. You see here, suppose what is the Laplace transform of this one? N factorial. N factorial means 2 factorial divided by s plus a. A here is 7. So s plus a n plus 1. N is a 2. 2 plus 1 is 3. Now, after obtaining the Laplace transform, if you substitute s is equal to j omega, you will get 2 by s plus s instead of s, we are substituting j omega, 7 plus j omega whole power 3. So we can easily obtain this Fourier transform from Laplace transform for this type of problems. So then after obtaining this Fourier transform, you need to calculate magnitude of h of omega. What is the magnitude of h of omega for this? Or h of omega whole square, whatever magnitude of h of omega, you can write h of omega complex conjugate of h of omega. That is the one way. Otherwise, you take a magnitude. What is the magnitude for this? There is no any imaginary part. So numerator is same. What is the real part? What does it mean? Real part here 7. What is the imaginary part here? Omega. So if we take a magnitude for this, root of 7 square plus omega square. This whole power 3 as it is there. Then if we squaring on both sides, if you squaring that one, 2 square is 4, root square gets cancelled. So finally we will get 4 divided by 7 square plus omega square whole power 3. Okay. Again, I am repeating this statement. What is the magnitude of h of omega? Magnitude means anything. There may be a real term and imaginary term. So root of real square plus imaginary square. In the numerator, there is no any imaginary term. So that is, we are not going to be distant. Even if you want to write here also, root of real square plus imaginary square. So anyway, imaginary part is 0. So you will get same term. Coming for denominator, there is a root of 7 square plus omega square. And there in the formula, we have a magnitude of h of omega whole square. Square root gets cancelled. So that is going to be right here. What is our formula? Syy of omega is equal to magnitude of h of omega whole square into sxx of omega. You observe this one, you compare this formula here. What is the formula here? 2 divided by 7 plus j omega. This is going to be replaced in place of 2 as it is 2. You see here 2 divided by 7 plus j omega whole cube magnitude whole square into this sxx of omega 3 divided by 49 plus omega square. Now coming for whatever my explanation. What is the squaring of this one? Magnitude of this one first before applying square. Magnitude of this one, then the real term is same. There is no any change. Coming for complex term, root of 7 square 49 plus imaginary part omega square root. So and then you apply square. Numerator there is a 2 square. Root square gets cancelled. And you will get the finally magnitude of h of omega whole square, it is this one. Now, along with that, there is a input or noise spectral density. That is a 3 divided by 49 plus omega square. Again, 49 means we can write this 49 like 7 square or as it is you can keep. So, you multiply numerator terms 4 into 3, 12. Denominator terms are same. So, you can write 49 plus omega square whole power 4, 3 plus 1. Now, after obtaining, it is what is the output power spectrum? What is the another question? Find the power spectrum of output. find the average power. Again, same. Average power of output. After applying the S by Y of omega, again, if you calculate inverse Fourier transform, if we calculate inverse Fourier transform, you know the inverse Fourier transform of S by Y of omega is equal to, it is nothing but R by Y of tau. So, R by Y of tau is equal to inverse Fourier transform of S by Y of omega is equal to 1 divided by 2 pi integral minus infinity to infinity S by Y of omega e power j omega tau into d omega. He has not written here clearly, but you write here. You write what is the formula? The explanation is, if you calculate autocorrelation function, then we can easily calculate. The average power. So the autocorrelation function is obtained from the spectrum is just inverse Fourier transform. So you write the inverse Fourier transform, and then wherever tau, Ry of tau, you replace tau is equal to 0. Whenever if you replace tau is equal to 0, there is an exponential term. This exponential term is going to be 1. So it is nothing but it is the formula. You can also say it is the area under the spectrum. 1 divided by 2 pi. Average value means area under the spectrum, because we are considering from minus infinity plus infinity this S by Y of omega entire spectrum, output spectrum we are considering. So area under the spectrum, we can also call it is a power. Now, S by Y of omega we have obtained here. You just copy. What is the S by Y of omega? 12 divided by 49 plus omega square whole power 4 into d omega. Again here you see that formula, we can write this is 7 square plus omega square. 7 square plus omega square, and there is a whole power 4. 7 square plus omega square whole power 4. So you can write this one 12 divided by 2 pi, again 1 by a tan inverse of omega by tan inverse of omega by a 1 by a tan inverse of omega by a you can write, and you can substitute that data here. Here you will get 516. I think this, because of this power 4, it is getting here. So you see this letter. This tan inverse of omega by a, you substitute these limits, you will get the pi. So it is about the, most of the time you may expect a problem, this type of problems, because the random noise power you will give, and there is an LTI system subjected to LTI system, and then we are going to be calculate output power or output spectrum like that. Now see, this is a network as given. Observe the network. A white noise with the spectral density N0 by 2, that is a SXX of omega, is transmitted through a linear system. As shown in figure. Find the output spectral density and average power. So it is simple a network. So before going to write it is in Fourier transform format, my suggestion is, my sincere advice is, better you write in Laplace domain. But he has given in frequency domain. Instead of doing the analysis, you write Laplace transform. What is the L? If you want, it is in, suppose the network is given in the time domain, here x of t, here it is a L, it is R, it is y of t. Now we can convert it is into S domain. It is going to be write x of s, it is going to be write SL, it is going to be write R, and it is going to be write y of s. First you convert this network into S domain. X of s, it is going to be write SL, it is going to be write, there is no any change in the resistance, and it is going to be write y of s. Then after converting this time domain network into S domain, because here already he has given in the frequency domain. So whenever if we substitute S is equal to j omega, sometimes he may not give in frequency domain. So at that time we are going to be convert this time domain into S domain first, and then we are going to be convert into frequency domain in the last. Okay, we are going to be converted to frequency domain in the last. Here in the network itself has given in the frequency domain. So after converting, my procedure is whatever the general procedure. Suppose is the time domain signal has given, you need to convert into S domain, and then in the last we are going to be converted into frequency domain. But in this case, he has given in the frequency domain. So wherever you have a S, S is going to be replaced with j omega or omega. So usually j omega. So you'll get x of j omega, and instead of S, S is equal to j omega. So SL is going to become j omega L. There is no any change in R. Y of S is going to be right, Y of omega. It is going to be right in the last after derivation. But anyway, in this problem, he has given in the network itself. Now, you see, the main point is what is the units of this L here. Now, it is suppose it is L is there, it is we are going to be called just inductance. Whenever we are going to be convert, whether it is in S domain, it is going to be SL, or it is in a frequency domain, it is going to be right j omega L. Now, we are not going to be called it is a inductance, it is going to be called inductive reactance. It is going to be called inductive reactance. So, whenever it is in the inductive reactance, the units are ohms. The units are ohms. Already resistance units are ohms. So we can apply here KVL. So for applying the KVL, definitely every element must satisfy Ohm's law. Every element must satisfy Ohm's law. That's why in the frequency domain or in S domain, we are going to be convert the given time domain signal, time domain element into the S domain or frequency domain. Now we can apply uh, KVL equation. What is the KVL equation? Applied voltage, suppose it is like input, applied voltage is equal to sum of voltage drops. So x of omega is equal to, suppose the current flowing through this one is I of omega. These two are in series. We can just add these two R plus j omega L into I of omega. So x of omega is equal to, you can write in separate paper, then only you can understand better. So you can treat like a input voltage. You can treat it is like output voltage. Then only you can get this problem because it is a network. There is a current is flowing. The input is a voltage. Output is also a voltage. Or you can take this is a current or this is also current. But we are assuming it is a input voltage. It is the output voltage. So applied according to the KVL, applied voltage is equal to sum of voltage drops. So this voltage is equal to, what is the current flowing through this one? You need to assume it is I of omega. So I of omega into j omega L plus I of omega into R. Then we take I of omega. What is I of omega? X of omega divided by R plus j omega L. Next, what is the Y of omega? Y of omega, current flowing through this resistor into this current, this resistor. What is the current flowing to this resistor? I of omega. So I of omega into R. Suppose it is equation 2. Previous equation is equation 1. Substitute this equation 1 in equation 2. I of omega in this equation. So what is the Y of omega? I of omega into R. What is the I of omega? Already we obtained. X of omega is equal to R plus j omega L into I of omega. Then I of omega is equal to X of omega divided by R plus j omega L. So Y of omega is equal to X of omega into, because this I of omega is X of omega divided by R plus j omega L into R. Then you write Y of omega by X of omega. It is equal to H of omega. So you don't confuse here. My idea is you treat it is a input voltage. It is the output voltage. Now the units of this inductance is ohms. The units of this inductance is ohms. Okay. Then we apply here KVL. You can apply here a KVL. So whenever if you apply KVL, you will get this one, H of omega. After obtaining the H of omega is equal to R divided by R plus j omega L. Are you getting? My point is, you just, it is a units of inductance is not a inductance here. It is going to be right inductive reactance. So this units ohms, simply apply KVL and find out the I of omega. And you need to find out the Y of omega. Y of omega is the current flowing through this one, I of omega into R. Then if substitute this I of omega here, you will get the Y of omega. Once if you get the Y of omega, and you can write Y of omega by X of omega, R divided by R plus j omega. If you take a magnitude, again, if you take a magnitude, here it is wrong. It is not R square. If you take a magnitude, just R. Here it is a root of R square plus omega square L square. Now, whenever if you write magnitude of H of omega whole square, it is not magnitude of H of omega, it is a magnitude of H of omega whole square. You correct it, this one. Sometimes there is in the book, there may be some mistakes. So this is a magnitude of H of omega whole square. First, you need to calculate magnitude of H of omega. For magnitude of h of omega in the numerator, there is no any real, there is no any imaginary part, it is as it is. In the denominator, there is a complex term, real term as well as imaginary term. At that time, you write root of real square plus imaginary square. What is the real term? R square plus omega L whole square. And then in our formula, we require magnitude of h of omega whole square. At that case, it is going to be get like this. So it is a magnitude of h of omega whole square. Now, the power spectral density of the output, SYY of omega. SYY of omega is equal to magnitude of h of omega whole square into SXX of omega. Anyway, it is the magnitude of h of omega whole square. It is not a magnitude of h of omega. So you just substitute this equation here. So you see SYY of omega, whatever the equation that is going to be substitute. He has given this input SXX of omega is a power spectral density, noise power spectral density N naught by 2. So you substitute here. And then he asked that after finding this, after finding the power spectral density, and you need to calculate average power. In the previous class and the just now also, where I explained, it is going to be applied area under the given spectrum, or we can calculate inverse Fourier transform of that particular spectrum, SYY of omega, it is nothing but RY of tau. After obtaining the RY of tau, you can substitute tau is equal to 0 in that. It is nothing but power. So that is we are representing here. This PYY means output average power, RYY of tau, at tau is equal to 0. That is the formula 1 divided by 2 pi integral minus infinity to infinity SYY of omega into d omega. So what is the SYY of omega? You substitute this for SYY of omega. Okay. Now it is R square, you write outside. Again, it is a 1 divided by a square plus omega L whole square. So 1 by a tan inverse of omega L by R, tan inverse of omega L by A. Then here in the numerator there is a R square, here it is a R. So finally, if we substitute these limits minus infinity plus infinity, so pi by 2 minus of minus pi by 2, you will get pi. So like that, you can calculate the average power. So it is about the problems on this unit. There's problems on this unit. We will see another topic also here. This again, I am going to discuss about this LTI system, because this entire unit is depends upon this LTI system. Okay, transfer function, how to calculate this transfer function of LTI system. Okay, now you consider it is an LTI system. The LTI system is linear and time invariant system. LTI system means linear and time invariant system, and its impulse response is h of t. For understanding purpose, he has given very clearly both time domain and as well as frequency domain. What is the time domain? X of t. It is the input. What is the characteristics of the system is given by h of t. And what is the output? Y of t. Suppose if we want to write in frequency domain, what is the Fourier transform of x of t? X of omega. What is the Fourier transform of h of t? H of omega. What is the Fourier transform of y of t? Y of omega. If we want to write, it is in time domain. Y of t is equal to convolution of x of t with h of t. Suppose if we want to write, the output is in frequency domain. It is nothing but convolution in time is multiplication frequency. Suppose it is a frequency, just we are going to be multiply. Suppose it is in time domain, we are going to write convolution operation between these two. So that's why very clearly he has given here. Now, individually also, suppose if you don't know this x of t, then it is not possible to find this y of t. So individual, suppose if you know the impulse response, you don't know the x of t, and if we want to find out our transfer function h of omega, we need output by input. Here, suppose he has not given input. At that time, sometimes he may give like that also. Find the transfer function of the system and he may give just output, he may not give input. At that time, you don't confuse here. Just you apply Fourier transform of impulse response. Suppose if you apply Fourier transform of impulse response, h of t Fourier transform is h of omega. It is equal to integral minus infinity infinity h of t into e power minus j omega t into dt. It is the general formula for finding the Fourier transform of h of t. It is nothing but transfer function of the system. Again, I am specifically repeating this word is this entire unit is depends upon this LTI system concept. This entire unit is depends upon LTI system concept. So, y of omega, if you want to obtain y of omega Fourier transform y of t, if you know directly y of t. If you want to obtain x of t, Fourier transform of x of t, suppose he has given the time domain x of t, you can calculate Fourier transform of x of t. Now, you see here, y of t is equal to convolution of x of t with h of t. And then if you apply Fourier transform on both sides. So Fourier transform of y of t nothing but y of omega. What is the y of t? Convolution of x of t with h of t. So convolution in time domain, in the frequency in the multiplication of the frequency domain, it is going to be right x of omega into h of omega. What is the h of omega now? H of omega is equal to y of omega by x of omega. You see here, it is nothing but transfer function of the LTI system or frequency response of the LTI system. It is very important. Frequency response of the LTI system or transfer function of the LTI system. Suppose he has given a transfer function of the system, he may ask the question is, find the impulse response of the system. Find the impulse response of the system. Whenever if you want to find the impulse response, you take inverse Fourier transform. You see here, the impulse response of the system can be obtained by taking the inverse Fourier transform of the transfer function. That is, h of t is equal to inverse Fourier transform of h of omega. We can write 1 divided by 2 pi integral minus infinity to infinity h of omega into e power j omega t into dt, d omega. So that's from that also we can calculate. Now, you see one problem. It is also similar to previous problem. You see this one. Okay, sometimes you may ask in the PTSP also, he may give simple these RC networks or RL networks, find the response or find the spectrum of output. Like that also you may expect the questions. You see here, find the transfer function of the network as shown figure. Find the transfer function. He has asked that transfer function of the system. So what is the transfer function? Y of omega by x of omega. So y of omega by x of omega, we need to calculate y of omega by x of omega. So for that, he has given it that system usually every time the problems, he may give this impulse response. This time he has not given, he has given the system. That system is a RC network. That RC network, from that RC network only, we are going to be calculate. So you see in the network, first one, R and C, these two are in parallel. And the second element is capacitor, with no issue with that. So whenever this R and C, previously also have given a process, whenever the signal, the given network is in time domain, the given network is in time domain, better you convert into S domain and then you go for frequency domain. Suppose if you want to convert it is in S domain, x of t Laplace transform is x of s. This C, one more thing, before going to convert this Laplace transform, I am going to specifically give why you are converting. What is the units of R? Ohms. What are the units of C? Farads. What are the units of C? Farads. But for applying KVL, we need for applying KVL, we need a units are in ohms, but the units are here farads. That's why we need to convert these units of farads into reactance. So that is going to be called capacitive reactance. That is going to be called capacitive reactance. So what is the mean by capacitive reactance, or what is mean by inductive reactance? What is mean by capacitive reactance, or what is mean by inductive reactance? Means capacitive reactance or inductive reactance, the difference is inductance separately. If we consider the inductance, the units are Henry. If we convert into reactance, the units are ohms. If we consider a capacitor, the separately if we consider capacitor, units are farads. If we convert into reactance, the units are ohms. Then only after converting the reactants only, we need to apply this concept of KVL. Okay, because KVL we need to, whenever we are going to apply KVL, that must satisfy Ohm's law. Whenever that element is not satisfying Ohm's law, it is not possible to apply KVL. Okay, it is the important point. ఈ క్లాస్ డిస్కనెక్ట్ అయితే మళ్ళీ మీరు 40 minutes తర్వాత డిస్కనెక్ట్ అవుతుంది. అగైన్ యూ జాయిన్. I will start again. You don't leave. I will continue this class up to 50 minutes. Okay. After 2 or 3 minutes, it is going to be stopped. Automatically stop this class. But again we will start. Whenever it is going to be convert into this capacitance into capacitive reactance, then only for that we can apply whether it is a Laplace transform or it is a Fourier transform for this network, for Laplace transform or Fourier transform. So that's why you see here this C1, what is the x of t, that is going to be, we have a doubt why every time we are going to be convert this time domain into Laplace domain or in Fourier domain. Okay, that is the importance. That is the importance. Whatever the capacitance, whatever the inductance, the units are henries and farads. So for converting these are units are into the ohms, we are going to be convert that given network into the, whether it is a Laplace transform or it is in the Fourier transform. So here, yes, directly converted into the Fourier transform. My point is better we convert into Laplace. So x of t Laplace transform is x of s, y of t Laplace transform of y of s. Whatever the current is flowing, that is I of s, usually I of t, that is going to be converted into S domain I of s. Whatever the C, that is going to be 1 by Cs, or there is no any change. Another C2 is also there, 1 by C2s. So 1 by C1s, you write in separate paper this network into the S domain, x of t Laplace transform x of s, y of t Laplace transform y of s. The current flowing to that one is I of t Laplace transform I of s. The C1 conversion is 1 by C1s, and R as it is same. C2 conversion is 1 by C2s. Why it is a 1 by C2 means, usually if you write a time domain equation, what is the voltage across capacitor? 1 by C integration of I dt. Suppose if you apply integration time domain property, Laplace transform of integration, you will get 1 by S. Suppose if you have a inductor, what is the inductor? What is the inductor? Time domain equation, V of t is equal to L into d by dt, d by dt of I of t. Now, if you apply time differentiation property of Laplace transform, you are going to get S. So that's why we are going to be right whenever there is a inductor SL, whenever there is a inductor capacitor 1 by CS. So this is the background of writing this SL and 1 by CS. Okay, are you getting my are you getting? If you want to write a time domain equation for inductor or time domain equation for capacitor, time domain equation for inductor is voltage across inductor is VL. Voltage across inductor is equal to L into d by dt of I of t. Now it is according to time differentiation property in S domain, we are going to write VL of S and L into d by dt of I of t is, what is the d by dt of I of t? S into I of S. So V of S by I of S, nothing but Z of S. Then there is a term we are going to get SL. Similarly, for capacitance, we are going to get 1 by CS. So we are writing here the equivalent impedance. Equivalent impedance means the units of impedance is ohms. That is we are obtaining from the frequency domain or it is in the time domain. So that is the clarity. Now, directly you see here, he has given after obtaining 1 by CS, I clearly said that there is a relation between Laplace transform and Fourier transform. Whenever there is a S, that is going to be replaced with j omega. Whenever there is a S, that is going to be replaced with j omega. So 1 by CS is going to be right here, wherever you have a S, j omega. Remaining, there is no change. Here also capacitance, that is going to be right 1 by CS. So whenever there is a S, j omega, because the Laplace transform Fourier transform relation. Now, after obtaining this, instead of showing this in the elements, better you show equivalent impedance. So what is the Z1 here? Parallel combination of this inductive capacitor reactance and R. And here there is no issue, we can write Z2. So that is going to be right here. What is the Z1? You need to obtain Z1. For our simplification analysis only, we are representing these are into Z1 and Z2, and then you separately calculate this Z1. So what is the Z1? Better, my point is you calculate in the S domain only all these things. Finally, after obtaining the H of omega, then only there you can substitute S is equal to J omega, then only it can easy for you. So here in the book, he has given in the starting itself this frequency domain. So I am explaining that concept only. Now, the parallel combination of these two, like R1, R2, you take it is like R1, you take it is R2. R1, R2 by R1 plus R2. You don't confuse here. It is like a resistor here because we are converting from capacitance to capacitive reactance. So units of capacitive reactance are ohms. So R1 is this, R2 is this, divided by R1 plus R2. It is the parallel combination of two resistors. So it is a Z1. Z2 as usual same, 1 divided by J omega into C2. Okay. So after applying this Z1 and Z2, you can write a formula, KVL formula here. It is the input voltage, it is the resistance, it is another resistance. So you can write KVL formula, applied voltage equal to sum of voltage drops. So what is the applied voltage here? What is the applied voltage? X of omega. What is the current flowing through this one? I of omega. So X of omega is equal to, these two are in series resistance, or you can write separately also. Applied voltage is equal to this voltage, sum of voltage drop, this voltage drop plus this voltage drop. So I into I of omega into Z1 plus I of omega into Z2. So what is the Z1? This I of omega is a common. So X of omega is equal to I of omega into Z1 plus Z2. So from that we can obtain I of omega. So I of omega is equal to X of omega by Z1 plus Z2. Okay, I of omega is equal to X of omega by Z1 plus Z2. After